Today our topic is projectile motion. So what exactly is it? Essentially, it is a form of motion in which an object thrown near to the surface of the Earth will travel a specific trajectory due to the effect of Earth's gravity. Let's say we're given a distance, indicated here with r, and asked to predict the trajectory of a dart fired at this point here in order to hit the target here. The horizontal component of velocity can be expected to remain constant throughout, as acceleration due to the Earth's gravity also remains constant. Firstly, we need the initial velocity. We know that height equals the initial velocity squared divided by the acceleration due to the gravity of Earth. So, we fired the dart assuming that the horizontal velocity was negligible. After several trials, the max height yielded was 1.312 meters. Substituting this into the formula allowed us the calculation of the initial velocity. The initial height in this case is simply 0, as it was assumed there was no horizontal component acting on the projectile as it was fired upward. So, in finding the initial velocity, what about the angle of launch? Using our understanding of trigonometry, we can solve for the initial launch height. We can see here the path of the projectile follows a path consistent with our understanding of a right-angled triangle, and we can see that the initial velocity follows that of the projectile's trajectory. Therefore, cos theta equals the distance indicated by Vx divided by the initial velocity, Vi, and sine theta respectively equals the height Vy divided by the initial velocity. Using a derivative of these two values, we can find the formula to yield the launch angle with the values given. Also, for a given range, there are two angles of projection, so over here, the equation is multiplied by 2 to account for the full trajectory of the projectile. Assuming our distance is equal to 1.65 meters, we can plug in the known values we have to get an angle of 19.48 degrees. Despite all our calculations though, we missed the target. Why might this be? There were a number of experimental errors throughout. Firstly was the vertical height we measured to find velocity. Despite conducting several repeated trials to yield height, the dart did not always fly vertically. That would allow us to calculate velocity assuming the horizontal velocity was equal to 0. The height of 1.312 meters was an average of all the observed values, many of which had a skewed upward projection, as I represented here. Calculating the uncertainty or degree of error through the calculation of the angle given the minimum and maximum values of height can allow us to view the possibility of quantitative error. There were significant differences in the height range of our projectile when fired vertically, roughly 5 centimeters above and below the average height of 1.312 meters. When these maximum and minimum values are substituted, we yield an error range of plus or minus 0.89 degrees. Considering the size of the target, which was 10 centimeters in diameter, this difference may have been the reason the projectile missed the target. Secondly, let's face it, we may be doing physics, but we aren't yet engineers. The structure we built to hold the dart launcher at a specific angle was not completely sturdy, and on occasion shifted during the firing of the projectile. Differences in height, or Vy, would have resulted in a different calculated initial velocity and therefore angle. Additionally, calibrating the angle of 19.48 degrees on the dart launcher proved to be a difficult task. Small variations in angle can have a substantial effect on the trajectory of the projectile, and ensuring that this angle is exact through the use of a protractor was not the most precise way to ensure the correct angle was set. So, in conclusion, if the experiment was conducted in a more precise manner, i.e. more trials were conducted to yield a more accurate height and velocity and so on, projectile motion will continue as expected and will hit the target given these values. Thanks for watching.